Hey guys, my name is IBM and I want to take you to the last lesson of electricity. I think this is going to be lesson 7, where we shall explore the most important but very abstract concepts of electricity and DC circuits. And in lesson 7, the most important concepts here will be potential dividers and potentiometers, where we shall mention the thermistor, we shall mention the LDR or the light dependent resistor, as we shall term them as sensors. We shall talk about a rheostat in more details, the potentiometers as potential dividers, where we shall talk about the potential divider formula. We shall talk about the graphs of the thermistor and the LDR, which are very important concepts in potential dividers. It's most likely going to be a very long lesson, but I'll try my level best to make it a little bit shorter. So this is going to be potential dividers and potentiometer, and I'm saying it is going to be the last unit or the last lesson of electricity and DC circuits. Okay, so this is lesson 7, and let us start. So the starting point of this is going to be the rheostat, potential dividers, and potentiometer. That is entirely what lesson 7 is about. The rheostat, we shall explore the rheostat in more details, or a variable resistor in more details. The potential dividers, where we shall talk about the potential divider formula, and we shall talk about the potentiometers, of course not forgetting the sensors such as the thermistor and the LDR. So what is a rheostat? We mentioned that a rheostat is a variable resistor. If you remember, when we were talking about resistance as a subunit, we talked about resistance where we considered a fixed resistor and a variable resistor. So we mentioned that a rheostat is a variable resistor. We saw the image of a rheostat, and you must be remembering the circuit symbol of a rheostat. So a rheostat is a variable resistor usually consisting of a coil of high resistance, wire connected to terminals, and a sliding contact which can be moved along the coil. I showed you the rheostat, I think that was in lesson 3 or lesson 4. So if a rheostat is connected in series with an item or equipment, the total resistance of the circuit may be altered by moving the sliding contact. So a rheostat has a sliding contact. Maybe I can show you a rheostat in the second slide. But we know that a rheostat is connected in a series with an item of equipment, and we are going to see the total resistance of the circuit could easily be altered by just moving the sliding contact of the rheostat, as we are going to see in our next slide. And since the voltage applied to the circuit is presumed to be constant, the rheostat provides a means of altering the voltage applied to the equipment, as we are going to see. So we are going to connect a rheostat, which is just a coil, which is made of a coil of wire, and the resistance of the rheostat could be just varied by just moving the sliding contact of the rheostat. And since resistance varies with length, moving the sliding contact means varying the length of the coil of wire of the rheostat, thereby changing the resistance. Therefore, a rheostat is going to act as a potential divider, or it is going to divide a given potential because total potential is presumed to remain constant. So when the fixed connections to the rheostat are connected across the supply, the appliance or equipment is fed from one fixed connection and a sliding contact. The device becomes a potential divider. So a rheostat is going to act as a potential divider. As the term stands, potential divider, it is going to divide the potential. Let's see what I mean by that statement. So let's consider this is a rheostat, and like I have said, it has we have already seen this. It has a sliding contact and it has a coil of wire on an insulated material. So this is what is connected to maybe a power supply, wherever it is. This is what is connected to the power supply. So by sliding this, say, to the left hand side, I'm reducing the length of the wire which is in the circuit. Therefore, I'm reducing the PD across that wire. I'm varying the PD across that wire. So if I want to connect this maybe to another device, I could have a device which needs the output from the rheostat, so that I can always move the sliding contact to change the PD, or the PD across the wire, which will be the PD across the component which we want to supply with energy, or to supply with the current to that effect. So rheostat is going to divide the power supply, or is going to divide the power supply to a certain amount. So it is going to act as a potential divider. So the rheostat is going to be used as a potential divider. And you remember the symbol, the circuit symbol for rheostat that we considered earlier on. If you recall very well, the circuit symbol for rheostat, we said the rheostat could be drawn as a fixed resistor like this one, and then we drew something like this. So this was showing a sliding contact, that the sliding contact would be moved along the length of the wire, which length of the wire is acting as a rheostat. So this is how the rheostat is going to work as a potential divider. By sliding the contact, we are varying the resistance. And because V equals to IR, if we are varying the resistance, then we are varying the PD across the wire of the rheostat. And therefore, the rheostat is going to be acting as a potential divider. So when resistors are arranged in series, they form what we call a potential divider. So it is like part of the connection of the resistance wire of the rheostat is going to be in series with the appliance. So this component here and this component are in series, and we are saying when resistors are arranged in series, they divide the potential. So they act as potential dividers. They divide the potential supplied to them in the ratio of the resistances. So we call them potential dividers. In your laboratory, you can try to carry out this experiment. In the laboratory, connect two resistors in series with a battery. You can try pairs of resistors which are the same, and pairs of resistors which are different. So you can say you can choose two resistors each of 5 ohms. Then you can choose a 5 ohm resistor and maybe a 6 ohm resistor, and then compare the results. So if you divide the PD across the resistors and divide the ratio of the resistances, you are going to notice that the ratio of the PD across the resistors is going to be the same as the ratio of the resistances of these resistors. For example, if I have 5 ohms and 6 ohms, I can predict that the PD across 5 ohms divided by the PD across 6 ohms is still going to be the same as 5 divided by 6. If you carry this experiment in the laboratory, you should be able to prove this. So you should be able to verify or to prove. Of course, if you're a teacher, you can guide your students through this activity in the laboratory, so that they're able to verify this scientifically or experimentally in the laboratory. So you should be able to establish the relationship V1 over V2 is equal to R1 over R2, which means the PD supplied is divided in the ratio of the resistances. So V1 being the PD across R1 and V2 being the PD across R2, where R1 and R2 are two resistors that you have chosen to investigate in the laboratory. The circuit you can connect in the laboratory is very simple. Have one resistor of say 5 ohms, have another resistor of say 6 ohms, and connect them across a power supply. Then connect a voltmeter across 5 ohms, connect a voltmeter across 6 ohms. Then divide maybe PD across 5 ohms by PD across 6 ohms. Then compare with the 5 divided by 6. You're going to find out that the ratio V1 over V2 is the same as R1 over R2, which leads us to the potential divider. But let's derive this expression scientifically. So this is what I'm talking about. You have two resistors in a series. Whenever two resistors, or whenever resistors, not necessarily two, they could be more than two. Whenever resistors are joined in series, I have said they make or they form what we call potential dividers. Whenever you have resistors joined in series, they form what we call a potential divider. That is very important. Every time resistors are in series, they form what we call a potential divider because they divide the potential of the power supply in the ratio of their resistances. So the voltage supply is V. The V is divided in the ratio of the resistances because remember V is equal to I times R. So the one with the bigger resistance will have a bigger value of V because in series the same current flows through each of the resistors. So first of all, the current through each of the resistor is the same, and I'm going to call it I. The total resistance here, because they're in series, resistance in series is the sum of the resistances of these resistors. If I consider Ohm's law, V equals to IR. So by Ohm's law, V equals to IR, and it means I equals to V over resistance. So in this case, the current is the e.m.f divided by total resistance. But remember, the e.m.f is V, and the total resistance is R1 plus R2. So this means the current I is going to be the supply, which is the e.m.f V, divided by the total resistance, which is V over R1 plus R2. If I want to find V1, then I will still use Ohm's law. V1 is going to be I times R1. That is V1. But remember, I is V over R1 plus R2. So if I substitute for I, it means that V1 is going to be equal to V divided by R1 plus R2, again multiplied by R1. So this means V1 is the same as R1 over R1 plus R2, then times V. And remember that this is the ratio of the resistance, R1, in comparison to the total resistance. In a similar way, if I want to find V2, I'll do the same. V2 will be equal to I times R2. And this will still give me R2 over R1 plus R2 times V. And therefore, it's like the voltage V, which is the voltage supply V, is being divided in the ratio of the resistance. The voltage supply V, or the e.m.f, or the supply from the battery, is being divided in the ratio of the resistances. That's why even for V2, we are getting V2 as R2 over R1 plus R2. These ones are called potential divider formula. These are the potential divider formula. So if I want to find the potential across a given resistor, I can get that resistor divided by total resistance times the voltage supply as long as the resistors are in series. And I'm saying this is the potential divider formula. However, if I divide these equations, divide V1 by V2. If you try to divide V1 by V2, dividing V1 by V2, if I try to divide V1 divide by V2, of course V cancels out and you remain with R1 over R1 plus R2. Remember, I'm dividing, so I'll say times, I get the reciprocal. V2 is going to be R1 plus R2 divided by R1. V2 is R1 plus R divided by R2. So I'm dividing the first equation by the second equation. So R1 plus R2 cancels out. And therefore, this gives me V1 over V2 as R1 over R2. That's why I say this is expected in the laboratory. So dividing the two equations therefore gives me V1 over V2 equals to R1 over R2. In an exam, if you have resistors in series, you have the voltage supply, you have the resistance of either of them, you can just use the ratio of their PDs being equal, the ratio of the PDs across each of them being equal to the ratio of the resistances, and you find the resistance of the other. Hence, I am saying A potential divider circuit is a source of variable potential difference. When someone talks about a potential divider or a potential divider circuit, is simply a source of variable potential difference. A source where the PD can be varied. That is a potential divider circuit. Or a source which has a variable potential difference. Let's look at a potentiometer in use as a potential divider. So instead of having two resistors in series, I now have a single resistor or a single wire which is acting as a resistor. However, I have a sliding contact, so this is going to be a rheostat. I can move the sliding contact upwards or downwards to vary the length of the wire into consideration, thereby varying the resistance of that part. So a potential divider may consist of a single variable resistor. It is a variable. In other words, its resistance can be varied. And by moving the sliding contact, we can achieve any value of voltage. So I could be having a load somewhere here. Instead of a resistor here, I could be having a bulb, which works at a certain PD. So I have to vary or move the sliding contact until the PD across this part here is the same is enough PD to light or to make this bulb to light if it was a bulb. So this means I can use the sliding contact to vary the resistance, thereby varying the PD, because this portion of the resistor here at the bottom will be in parallel with my component or my device. So it means the variable resistor here is acting as a potential divider. And when enough PD is reached to light the bulb, we expect the bulb to light in that case. So we are saying in potential dividers, the load is connected across a section of the divider whose PD is equal to the operating voltage of the load. The load in this case is what you connect here across the portion whose resistance or whose PD can be varied. And I say the load could be a bulb, it could be a cooker, it could be an electric lamp, and so on and so forth. So if we consider the load of resistance, say RL, if we consider a load of resistance RL connected with a certain section of our resistor or our variable resistor. So this portion of the resistor at the bottom here is in parallel with this load. They are in parallel. So it means the PD across this portion here is the same as the PD across this load here. Remember I said the load can be anything. It can be a cooker, it can be a bulb, it can be anything. So the load resistance, say RL, will now be considered to be in parallel with the resistance of the lower section of the divider. So because these two are in parallel, remember how we get resistance in parallel. So resistance in parallel will be R1 times RL over R1 plus RL. So this will be total resistance for these ones in parallel. But this form one resistor which is in series with R2, which means total resistance will be now R2 plus the resistance in parallel, which will be R1 RL over R1 plus RL. So this will be the total resistance in this case. Do not forget that this is going to act as a potential divider, and I said if, for example, we have a lamp, if I have a lamp connected here where we have our load, if I have a lamp connected here, and this lamp is only going to light when the PD across it is 5 volts. So it means I have to slide the contact to a point until the PD across the bottom section is 5 volts. That's when the lamp will light, because the PD across the bottom section is the same as the PD across the lamp. So as we vary this, as we move the sliding contact, we are varying the PD across the bottom section. And since it is in parallel with our load, then the load will light if we reach the required PD. However, these two sections of the resistor are potential dividers. They are dividing the power supply in the ratio of the resistances. And as we move the sliding contact upwards, we should be reducing R2, thereby increasing R1. And since V equals to I times R, as R1 increases, it means the PD across should be increasing. And therefore, we should be able to manipulate such concepts. So total resistance is going to be equal to R2 plus R1 RL of R1 plus RL. Note that I said when we have two resistors in parallel, we can find their effective resistance by simply looking at the product over the sum. Let's use this in an example. Maybe it will become easier to understand. So in the figure shows a potential divider V. A potential divider V is a high resistance voltmeter, which means its resistance is so high that the current here is zero. So current here equals to zero. If it is a high resistance voltmeter, remember for an ideal voltmeter, the resistance is infinite, which means the current going through it is approximately zero. A is an accurate ammeter. Find the ammeter and voltmeter readings. So first of all, to find the ammeter and voltmeter readings, I want you to notice that since no current goes through the voltmeter, these two resistors are in series. If they are in series, their total resistance is going to be equal to 20 plus 40, which is equal to 60 ohms. So if I want to find the current, remember the current is equal to the e.m.f divided by total resistance. So the e.m.f is 120, total resistance is 60, so the current is going to be equal to 2 amperes. If the voltmeter above was replaced voltmeter reading, that was the ammeter reading, then the voltmeter reading. Because no current goes to the voltmeter, so the reading of the ammeter is going to be the total current in the circuit. Then the voltmeter reading must be the PD across 40 ohms, because the voltmeter is connected across the 40 ohms. So because the voltmeter is connected across the 40 ohms, I can either use V equals to I times R, which will be simply 2 times 40, giving me 80 volts, or I can use the potential divider formula, which is the PD is the ratio of the resistances, which will be 40 divided by 40 plus 20 times the voltage supply, which is 120. This is the potential divider formula. I've used V equals to say R1 over R1 plus R2 times the voltage supply. That is going to be the PD across the 40 ohms, where R1 is 40, R1 plus R2 is 40 plus 20, and the voltage supplied is 120, which gives us the same answer, 80 volts. So you should be able to do that in an exam. So the voltmeter reading is going to be V1 because the voltmeter is connected across that point. So in our solution, we have seen the total resistance is 60. The current is the e.m.f over total resistance, and I could just use V as I times R to find the reading of the voltmeter. So this is the ammeter reading, and this is the voltmeter reading to that effect. But I said you could use the potential divider formula to find the voltmeter reading. Part 2 says if the voltmeter above was replaced by another voltmeter of resistance 120. Now this is no longer infinitely high. So it means we have another resistor in parallel with the 40 ohms because the resistance of the voltmeter is not so high. So some current flows into the voltmeter. What will be its new reading? Okay, so if some current flows through the voltmeter, what will be its new reading? And then part 3 tells us to find the percentage change in the ammeter reading. So we have to find the change in the ammeter reading and express it as a percentage. We have to find a new reading of the voltmeter. So let's try to do this. So now we have a voltmeter whose resistance is 120. This is not infinitely high, so it means some current flows into the voltmeter. So it means there is now a junction here where some current flows into the 40 ohms and some current continues to the voltmeter. So if I say the total current I, the total current I reaches here and part of it takes this path, let's call that one I1, and part of it takes this path, call this one I2. So current is dividing at that point. The current is dividing at that point. Or let me call this one I1 for consistency, and I'll call this one I2. So now these two 40 ohms and 120 ohms are like resistors in parallel. So we can find total resistance in parallel from product over the sum. Because there are only two resistors in parallel, I can get their total resistance from product over the sum. So product is 40 times 120 divided by the sum, which is 40 plus 120. So it means these two resistors, that is the resistance of the voltmeter and the 40 ohms, when combined, they give me 30 ohms. But 30 ohms will be in series with 20. So it means total resistance, our total will be 30 plus 20, which is equal to 50 ohms. So total resistance is 50 ohms, so I can find total current I. Remember, current is equal to the EMF divided by total resistance. So total resistance is 50, the EMF supplied is 120. So the current is going to be 120 divided by 50. That is going to be the current. So I'm saying that now the 40 ohms and the 120 ohm resistance of the voltmeter are in parallel. Even before they were in parallel, only that for the voltmeter it was infinitely high, that no current goes through it. But now that it is not as high as it was in the first part, so some current goes through it. Therefore, its resistance must be considered for this matter. So total resistance, we saw that total resistance is 50 ohms. And since the current is equal to EMF divided by total resistance, we shall just divide the EMF, which is 120, by total resistance, and we get the current as 2.4 amperes. That is not going to be the reading of the ammeter, not at all, because the current I, which is 2.4, divides at the junction. Part of it goes to the voltmeter because it has a low resistance, some current goes through it, and part of it goes into the 40 ohm resistor. However, I can find the PD across, I can find the reading of the voltmeter using either Ohm's law or the potential divider formula. Remember, the PD across 40 ohms is the same as the reading of the voltmeter, or the same as the PD across the 120 ohms, since they are in parallel. So from Ohm's law, from Ohm's law, V is equal to IR, where I is going to be the current through the whole of the resistance at the bottom, which is 30, which is simply going to be, if I want to find V1, I is going to be 2.4. If I use 2.4, which is total current entering the junction, then I should use the total resistance after the junction, which is going to be 30. In that case, V1 will be 2.4 times 30, which is 72. Alternatively, instead of doing that, I would get the PD across the 20 ohms. So I say V across 20 ohms is going to be the current, which is 2.4, because the 2.4 goes through that. It goes through 20 directly because it is linked to the battery. So it will be 2.4 times 20, and this gives us, is this 40? This is 48 volts. Then if I want to find the PD V1, which is the PD across 40 and at the same time the PD across 120, I would get 120, which is the voltage supply, minus 48, which is still going to be 72 volts. So this is another alternative of obtaining the same answer for the PD across V1. I could still use the potential divider formula directly, that is V1 will be equal to the resistance, which I will call R1 over R1 plus R2, then times the voltage supply Vs. But this time R1 is total resistance of the parallel combination, which is 30, divided by R1 plus R2, which will be 30 plus 20, then times the voltage supply, which is 120. And I'm certain the answer is going to be the same, because 30 divided by 50 times 120 is still 72. 30 divided by 50 times 120. So it is still 72. Okay. So the new reading of the voltmeter is going to be 72 volts. Remember, initially in part 1, the voltmeter reading was 80 volts. So it has reduced. By adding a voltmeter which has low resistance, its reading reduces, because there will be some PD across, or there will be some current which flows through its resistance. The PD reduces if some current is allowed to flow through the voltmeter. Okay. Then the other part was for us to find the percentage change in the ammeter reading. So we have to find the new current. In other words, we have to find I1. So remember Ohm's law, I is equal to V over R. So I can easily find the current I1. Because I already know the PD across 40 ohms, I1 is going to be V1 divided by R1 maybe. V1 is the PD across 40, which we have seen as 72. Then divide by the resistance there, which is 40. So the current is going to be 72 divided by 40, which I think is it 1.8, which is 1.8. Then I can find a percentage change. So this is 1.8. Then the change in current, I think in the part 1 we got a current of, 2 amperes. And in part 3, we are getting a current of, the reading of the ammeter as 1.8, so the change is going to be 2.0 minus 1.8. So we can now find a percentage change in current, which would be 0.2 divided by the original current, which was 2, then times 100. I think that gives us the percentage change in current. So from Ohm's law, we get the new reading of the ammeter to be 1.8. Remember, the first reading was 2.0 amperes. And then we find the percentage change in the current, which is 10%. Okay, so all that we are using potential dividers. Let's try another example. A battery of EMF 20 volts and 0 internal resistance is connected in the series with the two resistors R1 and R2 as shown. The resistance of R2 is 600 and this is fixed, so R2 is fixed. The resistance of R1 is varied from 0 to 400. Calculate the maximum PD. To have maximum PD, note that V is equal to I times R. We want maximum PD across R2. Using the potential divider formula, remember, PD across R2 is going to be equal to R2 divided by total resistance R1 plus R2, then times the voltage supply, which is V. So if we want V2 to be maximum, then the denominator should be small. Because R2 is fixed, then R1 should be 0. That is simple common sense. If we want V2 to be maximum, the denominator should be small. Because R2 is maximum, then R1 should be minimum, because R1 is the one which is variable. So R1 should be 0. So R1 should be taken to 0, therefore V2 for maximum, V2 is going to be equal to R2, which is 600, divided by 0 plus 600, then times the voltage supply, which was given to be 20. And I think this gives us 20. So the maximum is 20. In other words, no PD goes to R1. Then if I want minimum PD across R2, if PD across R2 is to be minimum, then the denominator should be maximum. So V to be minimum, the denominator should be maximum, and the denominator should be maximum if R1 becomes maximum. So this would be 600 over 6 over 400 plus 600 times the voltage supply, which is 20. So 600 over 1000, then times 20, I think this gives us 12. Okay, so that means using the potential divider formula, V2 is maximum when R1 is 0, which gave us 20, and V2 is minimum when R1 is maximum, which gave us the PD of 12 volts. Okay. The resistor R in the potential divider circuit has a resistance which varies between 100 ohms and 6.0 kilo ohms. Calculate the PD across R when its resistance is 100 ohms and when its resistance is 6 kilo ohms. Okay, even though I didn't want to solve this because I've given an example, I'll just try to do it. So the resistance R in the potential divider circuit has a resistance which varies between 100, so this varies between 100 to 6 kilo ohms, that is to 6,000, but this one is fixed at 1,000. Calculate the PDV across R when its resistance is 100. So remember, the V is going to be equal to R divided by R plus 1000, then times the voltage supply, which is 9. That is using the potential divider formula. So V is going to be, when R is 100, so this is going to be 100 divided by 100 plus 1000. Then I multiply this by 9. So 100 divided by 1100, then times 9. So this is 0.82. Then calculate the PDV across R when its resistance is 6,000. So in the second case, this was part A. So part B, V is equal to R is 6,000. Total resistance is going to be 6,000 plus 1,000, then times the voltage supply, which is 9. So 6,000 times 9 divided by 7,000. So that is 7.71 volts. So that is an easy question. The wire has length 1 meter and resistance 10 ohms. Use Kirchhoff's first law to state a relationship between I1, I2, and I3. So the first law was talking about the junction rule, that is the sum of currents into a junction is equal to the sum of currents out of a junction. I think this is direct. I1 equals to I2 plus I3. I think that one is direct. Calculate I1, and calculate the ratio X when X equals to the power in the metal wire over power in a series resistor. I think this is a past paper question which I quoted, but because it helped me to teach potential dividers, I decided to quote it. So we have to calculate I1. So where is I1? I1 is the total current. So they say the wire here is 10 ohms. This is 2 ohms and this is 2 ohms. These ones are in series and they're giving us a total of 6 ohms. 6 ohms is in parallel with 10 ohms. So total resistance is going to be 6 times 10 over 6 plus 10. We have 6 ohms in parallel with the 10 ohms. So we have 60 divided by 16. 60 divided by 16 60 divided by 16, that gives us, is it 60? The wire has length 1 meter and resistance 10 ohms. Use Kirchhoff's first law to state the relationship, then calculate I1. So 6 times 60. So 60 divided by 16, I think that is 3.75 ohms. That is total resistance. Then I1 is total current because it's just linked, is just coming from the battery. So I1, this is going to be the EMF divided by total resistance. So the EMF is 12. Total resistance is 3.75, which I'm very sure it should give us 3.2 amperes. So that one is direct. So these ones are easy. Calculate the ratio X, where X is the power in the metal wire over power in resistance, in a series resistance. X is the ratio of the power in the metal wire over the power in this series resistance. So of course we know that power is equal to I squared R. Because I don't know the current through the metal wire and I don't know the current through the resistance, the series resistance, I will not use that one. But I can also use V squared over R. Of course, the PD across AB is 12. It is the same PD across the series resistance. So the PD is the same down and above. So it means I can use this. What is just varying is the resistance. So the ratio is going to be the PD The ratio is going to be the PD, which is 12 squared, divided by the resistance of the metal wire, which is 10. Again, divide by the PD, which is 12, divided by the series resistance, which is a total of 6, because it's 4 plus 2. So that gives me the ratio, which is, I think it is going to be 0.6. So PD across SC is, of course, the length SC divided by the length AB times V. But of course, we know that the power is equal to V squared over R. Thus, X is going to be equal to, X is the ratio, remember, is the power across the wire AB, which is equal to V squared over R, resistance of the wire, then divide by the power across the series resistor, which is the PdV squared, divided by R, resistance of the wire. V is 12 because they're in parallel. The wire is in parallel with the series resistance of 6. So this is the same as, I just skipped one step there, it is the same as 12 squared divided by resistance of the wire was 10. Then divide by 12 squared, resistance in series was 6. So this is 12 squared over 10 times 6 over 12 squared. So this one cancelled out. That's how I came up with 6 over 10. So that is the ratio. Okay, so I will need this later on. Part B of the question, calculate the PD between point C and D. That is the only reason as to why I brought this question here. We want the PD between C and D. Okay, we want the PD between C and D. So we want the PD between these 2 points. So in other words, if we want the PD between these 2 points, we need to put a voltmeter here. So the voltmeter, of course, will compare the potential at this point with the potential at this point and give the difference. So how can I find the potential at this point? These 2 points have a common link at this point, at point A. So I can get the potential between A and C and the potential between A and D, and the difference between those two is going to be the potential difference between C and D. Alternatively, I can find the potential between C and B. potential between D and B, the difference between those potentials is actually going to be the potential difference between between C and D. Okay, so what is the PD across SC, which I'm going to call VSC? Of course, using the potential divider formula, PD across SC, the PD across SC, remember PD is equal to the current times resistance, but resistance is directly proportional to length. So it means the PD is directly proportional to length. And that's why we are going to later on see that the PD across a given section of a wire is directly proportional to its length. And in other words, because the PD is divided in the ratio of the resistances, and yet resistance is directly proportional to length, it also means the PD is divided in the ratio of the length. Therefore, the PD across SC is going to be the length SC divided by total length times the voltage supply, the voltage across the whole length. So the PD across a given section is divided in the ratio of the length of that section. So the PD here is going to be the length here. The length SC, which is given as 40 centimeters, divided by total length, which is 1 meter, that is 100 centimeters, then times the PD across AB, which is 12. That will give us the PD across SC. And if the PD across SC is obtained, then the PD across CB can be the balance, which could be 12 minus the PD across SC. Then the PD across AD, the PD across AD could be got from the current, say I3, the current I3, then times the resistance, which is going to be 4 ohms. However, we don't have the current yet. However, they gave us the current I3 to be 2 amperes. So if this is 2 amperes, then it means the PD across AD is going to be 2 times 4 from Ohm's law. That gives us the PD across 4 ohms. So the difference between those two PDs must be the PD across CD. So what I'm just saying is very simple, that the PD across SC is going to be the length S over total length of the wire times the voltage, or the PD across AB. So which is 0.4 divided by 1. 0.4 is 40 centimeters, then times 12, which gives me 4.8. Then the PD across AD is going to be I3. I3 times R, because the current through that section where we have a 4 ohm resistor is given as 2 amperes, so it is going to be 2 times 8. So the PD across this path is 8. The PD across the other path is 4.8. So the difference in those values is going to be the PD across CD. So the difference is going to be the PD across CD. Also, we could find the PD from the other end, from the right-hand side of the section, where I said you get the PD across CB or BC and the PD across BD. Of course, the current here is still 2 amperes. So the PD across DB is going to be 2 times 2, which is equal to 4 volts. So I now know the PD across BD. The PD across CB can still be got from, because if this is 40 centimeters, this would be 60 centimeters, because the wire is 1 meter. So I can get it from 60 over 100 times the PD across the whole wire, which is 12 volts. So that gives me another alternative for the PD across CD, and the answer is automatically going to be the same. Okay, so that was a past paper question, I think. I just quoted it from past papers and I decided to solve it here. Example 5. An LED is connected in series with a resistor to a 5 volts power supply. So the voltage supply is 5. Calculate the resistance of the series resistor required to give a current in the LED of 12 milliamperes with a voltage across it of 2 amperes of 2 volts. So we have an LED, that is a light emitting diode, is connected in series with a resistor to a voltage supply of 5 volts. Calculate the resistance of the resistor required, so let this be R, required to give a current in the LED of 12 milliamperes. Because they're in series, the current is going to be the same, 12 milliamperes, with a voltage across it. So the voltage or the PD across the LED is 2 volts. So the PD across the LED is 2 volts. So we want to find the resistance of the resistor. So you have two ways of doing this. You can use the potential divider formula, or you can use you can just do it normally using Ohm's law. But however, I know that V1 over V2 is going to be equal to R1 over R2 because these are resistors in series, so they are potential dividers. Of course, if the PD across the LED is 2, the PD across the R is going to be 3, that is 5 minus 2, which is 3 volts. So someone could say, okay, 2 for the LED over, we don't know the resistance for the LED, so we have two unknowns here. This may not work, but I can still find the resistance for the LED. Resistance for the LED, let me call it R1, is going to be equal to V over I, which will be 2 divided by 12 times 10 to the power of minus 3, because the current is in milliamperes. 2 divided by 12 exponent minus 3, which would be equal to 500 divided by 3. So I could say 2 divided by 500 over 3 being equal to R1. Sorry, I'm messing up this. I'm dividing the PDs on the left hand side, so it is going to be 2 divided by 3 is equal to 500 over 3 divided by R2, where R2 is the value for the resistance R. So if I just cross multiply this, I think 3 cancels out and I remain with 500 divided by 2, which is 250. Okay, if you don't want to do that, you can do this manually. For example, I can first find the PD across the fixed resistor is going to be 5 minus 2, which is equal to 3 volts. That's number one. Number two, the current is the same, which current is 12 milliamperes. That's number two. And resistance is equal to V divided by R, which is going to be 3 divided by 12 times 10 to the power of minus 3, which I'm very sure it is going to give us 250 ohms. So let me see, 3 divided by 12 exponent minus 3, that is 250 ohms. Calculate the PD across the LED when the series has a resistance 500 ohms. Calculate the PD across the LED when the series resistor, this is series resistor, has a resistance 500 ohms. Assume the resistance of the LED remains constant. So when the PD across the LED, if the resistance of the LED remains constant, so it means total resistance is is going to be the resistance of the LED, which is 250 plus 500, which is the resistance of the fixed resistor. Then the PD across the LED using the potential divider formula is going to be the resistance of the LED divided by total resistance times the voltage supply. So the resistance of the LED is 250. Total resistance is going to be 750 times what is supplied, which is 5. So 250 times 5 divided by 750. I think I used a wrong resistance for the LDR. I mean the LED. This was the resistance for the fixed resistor. It is not 250. I have to check this. I think I'm very tired now, yet I have a long way to go. I think the resistance for the LED was V, which was 2, divided by the current, which was 12 times 10 to the power of minus 3, which was 2 divided by 12 exponent minus 3, which was 500 divided by 3 ohms. That was the resistance. So this is going to be 500 divided by 3. So this is 500 divided by 3. 500 over 3 times the voltage supply, which is 5, divided by 500 over 3 plus 500. Okay, I'm just going to press my calculator here. 500 divided by 3 times 5 divided by 500 plus 500 over 3. Which gives me 1.25. You can also verify that. So I just use the potential divider formula for the second case. The new resistance, the resistance for the LED, remember, is 500 over 3 ohms. I just used R is equal to V divided by I. Okay. You can make your work very organized. May I just give you a hint? A variable resistor is used to control the current in the circuit as shown besides. The power supply has a negligible internal resistance. The resistance R of the variable resistor can be varied from 0 to 12. The maximum possible current in the circuit is 2 amperes. Calculate the minimum possible current. So if the maximum current in the circuit is 2 amperes, calculate the minimum possible current. Okay. So when do we have the minimum possible current? The minimum possible current, because current is inversely proportional to the resistance, then the resistance must be maximum. How do we have maximum resistance? The sliding contact should be somewhere here so that we have total resistance in series as R plus 6. So in this case, total resistance is going to be R plus 6, and R varies from 0 to 12. So this is going to be 12 plus 6, which is going to be 18 ohms. So the minimum current I1 is going to be equal to V, which is 12, over the total resistance, which is 18. So 12 divided by 18, so this is 2 over 3 amperes. So I think this is correct. Sketch a variation with R of current I1 in the circuit. So I can sketch this here just briefly. Variation of resistance with I1. So the minimum is 2 over 3. and the maximum is 2. So minimum is 2 over 3. Sorry, I'm sketching resistance C against. So this is going to be from 0 to 12. And the other one, current, is 2 over 3 and then 2. So when resistance is 0, the current is 2 over 3. No, that is not true. The minimum current is obtained when R is 12. So this starts from here. And when R is 0, the current is 2. So this is a graph of a decreasing gradient. So this is going to be a straight line with a negative gradient, because when R is 0, the resistance is maximum. The current is maximum, which is 2. And when R is 12, the current was minimum. So that is going to be a graph of that nature. When R is 12, the current was 2 over 3. When R is 0, when R equals to 0, the current is equal to 2. That's when we have the maximum. So that is a graph of a decreasing gradient. The variable resistor in A is now connected as a potential divider, as shown besides. Calculate the maximum possible and minimum possible current. So we can find the maximum possible and minimum possible current here. To have a maximum current, the resistance must be minimum. And how do we have minimum resistance? Is by having so when we bring this here, when we bring the sliding contact here, we cause what we call a short circuit. It means this one, we have made this to be R equals to 0, and when R equals to 0, the PD across R is 0. It means all the 12 volts is going to be the PD across 6 ohms. That is a short circuit. So it means 12 volts is going to be the PD across 6 ohms, since there is no PD across R, because we have created a short circuit. Therefore, it means the current through 6 ohms is going to be equal to 12 divided by 6, which is going to be 2.0 amperes. Then that is going to be the maximum possible current. Then, of course, the minimum current is, of course, going to be equal to 0. Sorry, I think I made a mistake here. When we cause a short circuit here, when R is equal to 0, remember these are supposed to be in parallel. So let me just change this, because we're not moving the sliding contact, but we are just changing the value of R. So when R equals to 0, if R equals to 0, it means the PD across R is 0. And because R is in parallel with the 6 ohms, the PD across 6 ohms is also going to be 0. And from current equals to V over R, it means that the current through 6 ohms is also going to be 0. So the minimum, I minimum or I2 minimum, is going to be 0. Then for the maximum, it means R is going to be equal to 12. R is going to be equal to 12 ohms. But remember, the PD across R is the same as the PD across 6 ohms. So it means I2 is going to be the PD, which is going to be 12 volts. If R is equal to 12 volts, the PD across it is going to be 12 volts. So it means the PD across 6 ohms is also going to be 12 volts. So this is going to be 12 divided by 6, which is equal to 2.0 amperes. So minimum is 0, maximum is 0. I have just argued this correctly. When R is 0, the PD across 0 resistance is 0. Remember, R is in parallel with 6 ohms. The PD across R is the same as the PD across 6 ohms. So if the PD is 0, then the current is 0. So the minimum is going to be 0. If R is 12, remember R is in parallel with the 6 ohms, but then it is also in parallel with the power supply. So if R is 12 ohms, the PD across R is the 12 volts, which is of the power supply, which is the same PD across 6 ohms. So that means the current I2 is the PD across 6 ohms divided by the resistance, which gives us 2 amperes. Okay. Yeah, I have 2 amperes and 0 amperes respectively. The answers are 2 amperes and 0 amperes respective. That is also a question I think I quoted from the past paper questions. You can try to think about it in that case. When R is 0, the PD across it is 0, but because it is in parallel with the 6 ohms, the PD across 6 ohms will be 0. From I equals to V over R, I2 will be 0. When R is 12, the PD across R is 12 volts because the power supply is 12. And because R is in parallel with the 6 ohms, the PD across 6 ohms is also going to be 12 volts. And therefore, the current I2 is going to be 12 divided by 6. Okay, I think that makes sense. Sketch IV characteristic of a filament lamp. I think this was something we discussed later or earlier on. Filament lamp. The IV characteristic, I said current against voltage. For a filament lamp, I said it is something, a graph of a decreasing gradient. Okay, so it's a graph of a decreasing gradient. The resistors of resistance 6 ohms is replaced with a filament lamp in the circuit of the figure A and figure B. So let's see figure A and figure B. Okay. State an advantage of using the circuit of the figure B when using the circuit to vary the brightness of the filament lamp. So they have replaced this with a filament lamp, I think. They have also replaced this with a filament lamp. So we have already seen that this one, when R is 0, the PD across R is going to be 0, which would mean the PD across the lamp will also be 0. So which means the current in the lamp is going to be 0. So it means this will be off. The lamp will be off. When R equals to 12, the PD across R is going to be 12 volts, which means the PD across the lamp is also 12 volts, which means the current in the lamp is going to be 12 divided by the resistance of the lamp. So this means it is going to be on or bright. So it means we have a full range between off and on for using circuit B. But using circuit A, we don't have off because the minimum was, I think the minimum, remember the minimum was 2 over 3 and the maximum was 2. So we don't have a full range. We just have between 2 over 3 and 2. Yet here we have between 0 and a certain value where 0 stands for off and the other one stands for on or full brightness. So the advantage of circuit B would be that we have full range of current or PD is possible for circuit B, or current or PD is possible down to 0. We can have the PD going to 0. So brightness ranges from off to full brightness for circuit B. Yet for circuit A, there is no off for circuit A because the minimum is 2 over 3, so the brightness does not go to 0. Okay, that is an advantage for using circuit B over circuit A. Okay, I think we should now talk about sensors maybe. Let's talk about sensors. We have application of potential dividers, that is in sensors. So sensors, or a sensor or sensing device, is a device which has a physical property that varies when there is change in whatever is being monitored. That is going to act as a sensor. So the most common sensors we are going to talk about here, or in this AS level physics, will be the temperature sensor, which we shall call, or we already know as a thermistor. And then we also have the light sensor, or the light dependent resistor, which we shall call, or is the LDR. These are going to be our sensors because they have physical properties which change with the change in whatever is being monitored. For example, the thermistor has its resistance, which is a physical property. It changes with the temperature. The light-dependent resistor has its resistance, which is a physical property, changing with the light intensity. So these are going to be called sensors. The symbol for thermistor, just to remind those of you who have forgotten the electronic symbols, for a thermistor, we showed a thermistor like that. And if you recall, an LDR, we represent an LDR like this. So this is the thermistor, and this is the LDR. Sometimes it will be drawn like this, sometimes it's drawn like this. The arrows are pointing towards the resistor to show that the resistance is depending on the light intensity. So these are going to be called sensors because a sensor is a device which has a physical property that varies with the change in whatever is being monitored. Let's begin by exploring a thermistor. So a thermistor is a kind of resistor whose resistance decreases as the temperature increases. So we shall call it a negative coefficient thermistor. It has its resistance decrease as the temperature increases. In other words, for a thermistor, resistance is inversely proportional to temperature. Recall, for a normal device, a normal metal conductor, we saw that the resistance was directly proportional to temperature. However, we are seeing that a thermistor has its resistance inversely proportional to temperature. Normally, it is only semiconductors or materials made from semiconductors that have their resistance vary inversely proportional to temperature. So most likely the thermistor is made out of a semiconductor. So such a thermistor is going to be called a negative temperature coefficient thermistor. Why do we call it negative coefficient? In this case, we are calling it negative coefficient because its resistance goes down when the temperature goes up. In other words, resistance decreases as the temperature increases. That's why it is called negative temperature coefficient thermistor. So a thermistor is generally made out of a semiconductor, normally silicon. We have semiconductors such as germanium, but commonly it is silicon. And we know that a semiconductor is a device that has conductivity. Its conductivity is between that of an insulator and most metals. So it is in between there. In a unit called band theory, which was scrapped from the syllabus, you would understand what really happens when semiconductors are connected in a circuit. We have what we call the valence band, the forbidden band, and the valence band, forbidden band, and the conduction band. Semiconductors have their electrons in the valence band. These electrons do not have enough energy to move into the conduction band, so they do not conduct under certain temperatures. But as temperatures increase, these electrons gain enough energy to cross the forbidden band to the conduction band so that the material can conduct. So semiconductors have their resistance decrease when temperatures increase. Their resistivity, their conductivity is between that of metals and, most metals and insulators. So it is in between there. That is a thermistor. So one property of a semiconductor is that when the temperature rises, the number of free electrons increases and thus the resistance decreases. In other words, the number of free electrons with enough energy increases. That's why we say more electrons move into the conduction band. But that is the band theory, where band relates to a range of energies. So at high temperature, more electrons have enough energy to move freely, and therefore the material is said to conduct. That's why we are calling it negative temperature coefficient. Okay, of course we can use a thermistor as a sensor because we are saying these are sensing devices. So to connect a thermistor as a sensor, we must put it as a potential divider. Remember, when resistors are joined in a series, they form what we call a potential divider. So to be used as a sensing device, to use a thermistor as a sensing device, the thermistor must form part of a potential divider like the one I've just shown here. So we have a fixed resistor in series with the thermistor. Remember, the thermistor, its role is going to tell us whether there is a change in the temperature of the surrounding. How do we know that there is a change in temperature of the surrounding? We could connect an indicating lamp, maybe in parallel with a fixed resistor or in parallel with the thermistor. So let's say we have a lamp here, which will indicate if there is a change in temperature. Remember, when the temperature increases, the resistance is expected to decrease. If the temperature decreases, the resistance is expected to increase. Suppose we have the lamp here, which is just able to light if the temperature falls below a certain value. So if the temperature falls below a certain value, we expect that the resistance of R is going to increase. So the PD across R increases, which means the PD across the lamp increases until it reaches a certain value. If the PD is say 5 and the lamp lights at 5 volts, then the light is going to be seen going on to indicate that there has been a fall in temperature. So the thermistor at that point will be acting as a potential divider and as a sensor. So the potential divider, or the PD, is divided between the resistor and the thermistor. And as the temperature increases or as the temperature rises, the resistance of the thermistor decreases. So it means the PD across the thermistor decreases because from V equals to IR. Since the resistance of the thermistor decreases at increased temperature, the PD across the thermistor decreases. But remember, the voltage Vs is divided between the thermistor and R. If the PD across the thermistor decreases, it means the PD across the fixed resistor must increase because the total should remain Vs. So as the temperature rises, the resistance of the thermistor decreases. So the PD across it decreases. However, as the PD across the thermistor decreases, the PD across the fixed resistor increases. That means the PD across the fixed resistor increases as temperatures increase. So this means the PD across the fixed resistor increases as temperature increases. For a fixed resistor, it is going to be increasing. If I try to sketch a graph of our resistance against temperature for a thermistor and I compare it with a metal wire, the resistance of temperature, the graph of our resistance versus temperature for a thermistor and a metal wire. For a thermistor, we have seen that the resistance is inversely proportional to temperature. But remember, for a metal wire, we saw that resistance was directly proportional to temperature. Note that in both cases, the graphs do not start from zero because all materials have some resistance even at the lowest temperature, even at 0 degrees Celsius, they have some resistance. That's why these graphs do not start from zero. The gradient of the metal wire was very small because the change in resistance with the temperature is not very rapid, it's not very big. So that's why the gradient is very small. So the graph for a thermistor, resistance is inversely proportional to temperature. The resistance does not vary linearly for a thermistor because the thermistor is made out of a semiconductor. Where a semiconductor, not all the electrons gain enough energy uniformly to become free. That's why it is not going to be a straight line. So if the source voltage and R are known, the temperature can be got from the graph shown here. So if I know the voltage of the power supply I can use the voltage of the power supply to get the resistance. And if I know the resistance, then I can use the resistance to find the temperature. If I know V, I'll find the resistance. If I obtain the resistance of the thermistor, then I can find the temperature from the graph. Okay, so we are still exploring the thermistor. Hence, a thermistor can be used as a sensor because the resistance of a negative temperature coefficient thermistor decreases as its temperature increases. It can be used as a sensor because the physical property, which is resistance, it decreases as the temperature increases. For a metal wire is not a negative temperature device. For it, we have seen that the resistance increases as the temperature increases. So for a metal wire, it could be used as a sensing device too, but in a different way. For it, it can be used as a sensing device still because it has its temperature vary with the resistance, or resistance vary with the temperature, but cannot be used in the same way as a thermistor because for it, for a thermistor, it will cause an increase in resistance when the temperature decreases. Yet for a metal wire, as the temperature increases, the resistance also increases. So in that case, therefore, a thermistor is going to be more useful than a metal wire because there is a much larger change in resistance with a change in temperature for a thermistor than for a metal wire, as we have seen from the graph. You have seen the gradients. For a metal wire, it was just a line whose change in gradient or whose gradient was relatively smaller. But for a thermistor, we saw a deep change in a deep fall in the slope, indicating that for a thermistor, the gradient is going to be bigger than the gradient for a metal wire. Therefore, a thermistor may give a more precise value for change in temperature as compared to that of a metal wire. So a thermistor is more useful than a metal wire because there is a much large change in resistance with the change in temperature for a thermistor than for a metal wire, as we have seen from the graph. So the examiner will ask you explain why a thermistor would be better for measuring change in resistance in comparison to using a metal wire. A thermistor is more useful than a metal wire because there is a much larger change in resistance with the change in temperature as compared to that for a metal wire. That's why a thermistor would be better. Okay, let's also first talk about the LDR, or the light dependent resistor, which is also going to be negative coefficient, but this time it will not be temperature, it will instead be light, negative light coefficient. So the LDR, it is also made up of a semiconductor just like a thermistor, and it has its resistance. LDRs have a resistance which changes in the response to changes in the light levels as detected by a photosensitive plate on the resistor. So the resistor has a photosensitive plate, or a plate which is sensitive to light. You must be having LDRs in the lab, so you should be able to shine some light onto them and see what happens if you connect them in a circuit. And most LDRs, just like thermistors, are negative light coefficient, meaning their resistance decreases as the amount of light or the light intensity falling on them increases. That's what qualifies them to be negative coefficient. Their resistance decreases as the light intensity increases. So resistance is inversely proportional to the light intensity for the LDR. That's why we are going to call them negative coefficient. Negative light coefficient LDRs. So if we want to use them, of course, still we shall also connect them into what we call a potential divider. So LDRs are used in light detection circuits. These are going to be used as potential dividers the way we have done with thermistors. So the intensity of light can be measured with a circuit shown here. So we can detect or we can measure the intensity of light using the circuit. But what is very important for us to note is that just like the one for the thermistor, we have two resistors in series. Although one resistor has its resistance vary with the light intensity, which is the LDR. So we can connect a lamp in parallel or across the LDR if you want, or an indicating device here, which can help us to tell that there has been a fall in light intensity or there has been an increase in light intensity where the lamp can switch on and off. But we have mentioned that just like the thermistor, the LDR has its resistance decrease as the light intensity increases. Thus, LDRs can also be used as sensors. For example, uh, security lamps in cities can switch themselves on at night and switch themselves off in the morning by just using LDRs. Maybe when it is at night, the light intensity across the LDR decreases, and so maybe the PD across the LDR goes down. So the lamps, the switch which switches or which turns on the lamps could be connected across the fixed resistor, or it can also be connected across the LDR that when the PD across the LDR falls below a certain value, the switch turns itself on to turn on the security lights. So it will be acting as a sensor, turning on and off depending on the light intensity falling on the LDR. So the LDR can be used as sensor because its resistance decreases as the incident light intensity increases. Hence, it can be used as a potential divider. So the potential of the power supply can be divided between the resistance of the LDR and the resistance of another fixed resistor. So the graphs for resistance against temperature and resistance against light intensity have the same shape. Resistance decreases as temperature increases for a thermistor. Resistance decreases as the light intensity increases for the LDR. Example. The resistance plotted against the light intensity for an LDR is shown below. Use the graph and the figure above to calculate V out when the light intensity is 60 lux. What is the voltage across the 3 kilo ohm resistor when the light intensity is 10 lux? Remember, these are going to operate the same way we consider potential dividers. So this should not be just something confusing. So first of all, we want to use the graph to calculate V out. V out is across the LDR or the light dependent resistor. So let this resistance be R of the LDR. So from the graph at 60 lux, the resistance of the LDR is, use the graph to find, use the graph and the figure above. This is supposed to be the figure below to calculate V out when the light intensity is 60 lux. So when light intensity is 60 lux, the resistance is 20 ohms. So the resistance of the LDR is going to be 20 ohms. So if we use it as, if we consider potential divider, then V out is going to be the resistance of the LDR, which is 20 over total resistance, which is 20. Remember, this is in kilo ohms. So it is going to be, this is 20 kilo ohms divided by 20 plus 3, which is 23 kilo ohms, then times the voltage supply, which is 10. So 20 over 23 times 10, 20 divided by 23 times 10. So this is going to be 8.7 volts. So that is V out is going to be 8.7. What is the voltage across 3 kilo ohm resistor when the light intensity is 10 lux? So when the light intensity is 10 lux, the resistance from the graph is 100. So we just change this to 100. So we shall say V out What is the voltage across 3 kilo ohms when the light intensity is 10 lux? So the resistance here is going to be 100. So I can still use the potential divider, but I want a V out across 3, not across the LDR. Part A was across the LDR, but this is now across 3. So I'll say 3 divided by, at 10 lux, the resistance of the LDR is 100 kilo ohms. So it is going to be 3 plus 100, which is 103 kilo ohms. Then times the voltage supply, which is 10. This gives us so this is giving me 0.29 volts. So the PD across 3 kilo ohms is going to be 0.29, and of course the PD across the LDR would now be 10 volts minus 0.29. Okay, so if I wanted the PD across the LDR, I would just say 10 minus 0.29, which will give me the PD across the LDR alone, which will be now my V out. So that is how we use the potential dividers together with the sensing devices in calculations. Okay. So I think I've got 8.7 for V out, and then the PD across 3 kilo ohms, I go to 0.29. If I wanted the PD across the LDR in the second case, it would be 9.71. So the potential divider formula could also be used as I have used it here directly to get 8.7. You could still use it directly every time you want. Okay, example. Let's continue this example. The circuit shown above produces a decreasing output voltage when the light intensity increases. So the circuit we have above, the circuit we have seen from the previous slide, is producing a decreasing output when the light intensity increases. Note that V out is connected across the LDR. And here they are telling us that when the light intensity increases, the PD across V out is decreasing. How can this circuit be altered to produce an increasing output as light intensity still increases? This circuit is producing a decreasing output when light intensity increases. But we want the same circuit to produce an increasing output when light intensity increases. So the only way we can do this is to swap the LDR and the 3 kilo ohm resistor. We swap the positions, because we notice that if we swap the positions, we bring the LDR here and we bring the 3 kilo ohm resistance here. As light intensity increases, the PD across the LDR is going to decrease, which means the PD across the 3 kilo ohm resistor will increase. And if V out is measured across the 3 kilo ohm resistor, V out will be increasing when light intensity increases. So the easiest thing would be to swap the 3 kilo ohm resistor with the LDR, to swap the positions, or to measure V out across the 3 kilo ohm resistor. It is the same thing. So the easiest way to do this would be to swap, or to simply measure V out across the 3 kilo ohm resistor instead of the LDR. So the easiest way is to swap the 3 kilo ohm and the LDR resistor positions. Alternatively, you can take the output of V out measured across the 3 kilo ohm resistor. You can also, by the way, use an inverting amplifier, but this is beyond our syllabus by now. We could use an inverting amplifier or an inverting operation amplifier, but this was scrapped out of the syllabus. It used to be in the electronics. The easiest is to swap the 3 kilo ohm resistor and the LDR, because V out was initially measured across the LDR, and if V out is measured across the LDR, when the light intensity increases, resistance of the LDR decreases, and means V out also decreases for the LDR. So if we want the light intensity to increase and V out to also increase, then we must make sure V out is measured across a fixed resistor, whereas the PD across the LDR decreases, the PD across the fixed resistor increases. Okay, I think that makes some sense. Example 2. A battery of EMF 12 volts and negligible internal resistance is connected to two resistors and a LDR as shown. An ammeter is connected in series with the battery. The LDR and the switch S are connected across the points XY. The switch S is open. So S is open, capture the PD across XY. Of course, if the switch S is open, this is the LDR is out of circuit. And that it makes this very easy. So total resistance R total is going to be equal to, these will be in series. So it will be 12 plus 8, which is 20 kilo ohms. And I want to find the PD across XY. If I want to use the potential divider formula, V across XY is going to be the resistance there, which is 12, divided by total resistance, which is 20 kilo ohms, then times the voltage supply, which is 12. So this gives me 12 times 12 divided by 20. I think that is 144 divided by 2. That is 7.2 volts. So that is 7.2 volts. The switch S is closed. Now when we close the switch S, we now have two resistors in parallel. The resistance of the LDR is 4 kilo ohms, capture the current in the ammeter. So now that we have two resistors in parallel, their total resistance here, resistance in parallel is going to be 12 times 4 divided by 12 plus 4, which is going to be 48 divided by 16. I think that is 3. So this is 3 kilo ohms. So we have 3 kilo ohms in parallel, but the parallel resistor of 3 kilo ohms is going to be in series with 8 kilo ohms, which means now the total resistance becomes 3 divided by 8, which is 11 kilo ohms. And therefore, if I want the current, the reading of the ammeter is the total current from the battery. So the current I is going to be equal to the EMF divided by total resistance, which is going to be 12 divided by 11, which I think this is 1 point something. 12 divided by 11, 1.1 times 10 to the power of minus 3 amperes. So the current here is 1.1 times 10 to the power of minus 3 amperes. So I think that one is fine. That is the reading of the ammeter, which is the total current. The switch S remains closed. The intensity of the light dependent resistor is increased. So light intensity increases. State and explain the change to the ammeter reading. So if the light intensity increases, it means the resistance of the LDR decreases. The resistance of the LDR decreases. Remember, total resistance, what happens to the resistance in parallel? If the resistance of the LDR becomes smaller, it also means the resistance in parallel decreases, which also means total resistance in the circuit also decreases. If the total resistance in the circuit decreases, remember total current is EMF over total resistance, so it means total current increases. So it means the ammeter reading is going to increase. 1. If the light intensity increases, the resistance of the LDR decreases. The resistance in parallel, that is the LDR and the 12 kilo ohms, decreases. To find total resistance, we get the resistance in parallel plus the fixed resistance of 8 kilo ohms, which decreases. But total current, which is the reading of the ammeter, is EMF over total resistance. So the total current increases because the total resistance has decreased, since current is inversely proportional to resistance. So we have seen that the reading here increases. Then the PD across XY, the PD across XY. So because the current has increased, the PD across the 8 kilo ohm resistance has increased. So PD across 8 kilo ohm resistance increases because it is in series with the ammeter. So all the current is going through 8 kilo ohms before it divides into the 12 kilo ohms and the LDR. So if that PD increases, it means the PD across XY must decrease because the total must not go beyond 12 volts. So because the PD across 8 kilo ohms has increased, then the PD across XY must decrease. Alternatively, the resistance, you can talk about the resistance. The resistance in parallel has decreased, and the PD across XY depends on that resistance in parallel. Since the resistance in parallel has decreased and V equals to I times R, so it also means that V across XY must have decreased. So you can say the resistance across X of XY, which is total resistance in parallel, has decreased. And it is directly proportional to the PD, so the PD across XY has decreased. Very simple. So in our solution, I've just solved this very easily. The first one, we got PD as 7.2, resistance 20. Parallel resistance was 3 kilo ohms. We got the total resistance as 11 kilo ohms. And the current reading of the ammeter was 1.1. Then in part C, the total resistance of the circuit becomes smaller because we say the resistance in parallel, when the light intensity increases, resistance in parallel decreases, total resistance decreases. And because current is equal to e.m.f divided by total resistance, the current, because this decreases, the current increases. So we saw that the current increases. Then our resistance across XY is proportional to the PD. Resistance is less, hence PD is going to be less. So if the light intensity increases, the resistance across the parallel decreases. And remember, V across XY is depending on the resistance in parallel. Is going to be current times the resistance in parallel. Since this decreases, the PD across XY also decreases. Or you can say as current increases, the PD across the 8 kilo ohms increases, which automatically means that the PD across XY must decrease because the total should remain 12. As simple as that. A potential divider consists of a battery of e.m.f 6 volts and negligible internal resistance connected in series with a resistor of resistance 120 ohms and a variable resistor of resistance between 0 and 200 ohms. Determine the range of potential differences that can be obtained across the fixed resistor. So I can just try to sketch this. We have a potential divider which consists of a battery, negligible internal resistance in series with a fixed resistor of 120 ohms and a variable resistor between 0 and 200 ohms. Determine the range of potential differences that can be obtained across the fixed resistor. So we want the PD across the fixed resistor using the potential divider formula. V out is equal to R1 over R1 plus R2 times the voltage supply. So we can have V across 120, which is the fixed resistor, could be 120 divided by when the other one is 0, so it will be 120 plus 0 times 6, which is 120, which is equal to 6 volts. Then when the other one is 200, V could be equal to 120 over 120 plus 200 then times 6. 120 divided by 320 times 6. This is 2.25 volts. So the range is from 2.25 to 6. So in my solution, I said when the variable resistor is at 0 ohms, the PD across the fixed resistor is going to be 6 volts. And when the variable resistor is at 200 ohms, the PD across the fixed resistor is 2.25 volts. So the range we are talking about is between 2.25 volts to 6 volts. Self-check. In order to switch on a heater when the temperature falls below a set value, a potential divider is connected to a switching circuit. When the input voltage to the switching circuit falls below 0.5 volts, it switches the heater on. Copy the figure and add a suitable potential divider circuit to trigger the switching circuit. Okay, so I'll just add a potential divider here. In order to switch on a heater when the temperature falls below a set value, a potential divider is connected to the switching circuit. So I'm going to have when the input voltage to the switching circuit falls below 0.5, it switches the heater on. So you need to have a potential divider. So the PD across this should fall. So I'll put this across the switching circuit. So the PD across this should fall to 0.5. I could put here, let me just put here, because they didn't specify, it is temperature. In order to switch on a heater when the temperature falls below a set value, so the temperature must be falling. If the temperature falls, the PD across increases. So I can't put the thermistor here, I must put it here. Because when the temperature falls, when temperature decreases, resistance of the thermistor increases, which means the PD of the thermistor increases. Yet we want the input voltage to the switching circuit falls below 0.5, it switches the heater on. So it means we must ensure that the PD falls. So we can't put a thermistor here because when the temperature falls, the PD will just be increasing instead of falling to 0.5. So I'll put a thermistor here. So that is where my thermistor is. So here I'll put a fixed resistor. Because when the temperature falls, the resistance of the thermistor increases, the PD across the thermistor increases. So it means the PD here, the PD of the fixed resistor decreases, and when it reaches 0.5 volts, it switches the heater on. So here I have a voltage supply. I have a fixed resistor which is in parallel with the switching circuit. So this is how the circuit should look like. I can't put a thermistor here because if the temperature falls for a thermistor, the resistance increases. And if the resistance increases, it means the PD across the thermistor just continues increasing. Yet we want it to switch on the heater when it falls below 0.5. Okay. Explain how the operator could lower the temperature at which the heater is switched on. So how will the operator lower the temperature at which this heater is going to be switched on? So one, we could use a smaller voltage supply, a smaller value of V. A smaller value of V means the PD across the thermistor and the fixed resistor is low. So it means we can easily fall below 0.5 volts at a very small temperature. So decrease V. decrease the voltage supply, or use a smaller voltage supply. Number two, you could use R should be small. R should be decreased. Because if R is small, it means the potential would easily become smaller in a very short period of time uh, before the temperature is big enough. Okay. Then maybe lastly, let's talk about potentiometers. Having seen sensors, let's talk about potentiometer circuits briefly. So what is a potentiometer? We have seen potential dividers, and we mentioned that whenever we have resistors in series connected across a power supply, they form what we call a potential divider because they divide potential. So a potentiometer can also be a potential divider, but this is going to be a specific type or a modified type. So a potentiometer can be thought of as a type of potential divider circuit. However, it is going to basically be used to compare EMFs and PDs. It is still a potential divider, but basically it is going to be used to compare EMFs and PDs. And mostly we shall be talking about a slide wire potentiometer. We shall be talking about a slide wire potentiometer, which consists of a driver cell and a uniform resistance wire, let's say wire AB, which is normally either constant 10, it could be copper, it could be nichrome. You should be able to connect a potentiometer in the laboratory. So the purpose of the driver cell is to maintain a steady current through the wire, and hence to maintain a PD across the wire to a stable value. So a potentiometer can look like this in the laboratory. So this is the standard form of a potentiometer where you have a driver cell which maintains a constant PD across the wire. This is a sliding wire over which a contact can be moved. And the sliding wire or wire of uniform length, uniform resistance is connected in parallel or across the cell. Remember, resistance is directly proportional to the length of the wire if it is a uniform wire. And if the wire is connected across the cell, the PD across the wire AB is the same as the driver cell or the EMF of the driver cell. So the first thing we can do is to find a PD per unit length of this wire. After all, resistance is directly proportional to length, and V is equal to I times R. If the current is a constant, the PD is directly proportional to R, and because R is directly proportional to L, it means that the PD is also directly proportional to the length. So we can find a PD per unit length of this wire, and if it is a constant, since the wire is uniform, then we can use that PD to find anything else that we want. So the PD per centimeter in this case, or per unit length, is going to be constant if the wire is uniform, which is going to be the PD across AB divided by the length AB. If the voltage supply is V, or the EMF of the driver cell is V, which is the same as the PD across AB, then the constant, which is the PD per unit length or PD per centimeter, is going to be V divided by the length of the wire. So the PdVx of any length of the wire can now be found by just multiplying the PD per unit length times the length. After all, the length is directly proportional to the PD, or the PD is directly proportional to the length. So if I know the PD per unit length, then I can always find the PD for any length of this wire. That is how a potentiometer works. If I know the PD per unit length of the wire, then I should be able to find the PD for any length of the wire. That is how a potentiometer works. And therefore, there is a relationship between length of the wire and the PD. There's a relationship between the length of a given wire, or the length of the wire, and the PD of the wire. So if I know the PD per unit length of the wire, then I can always find the PD of any section of the wire. Let's talk about what we call standardization. So to standardize or to make a potentiometer ready for use. So one, remember I said the potentiometer is going to be used to compare EMFs and PDs. So the first thing we are going to do is to use the potentiometer to compare, for example, EMFs, or find a relationship between EMF and lengths of a uniform wire, of the wire of a potentiometer. So here we have a uniform wire labeled AB, whose length is, let's say, LAB. So the length of the wire is going to be LAB. And we have connected it across a driver cell whose EMF is E0, the driver cell. So the only thing we need to add here is we are going to add a voltmeter, because we are going to employ what I call the null method of taking a measurement. So a potentiometer is going to use what we call the null method of taking a measurement. I talked about the null method when I was starting electricity in lesson 1, where a measurement is going to be correct if an instrument gives no reading. So I may want to compare the EMF of the unknown cell EX with the driver cell E0, or I may want to find the EMF EX of the unknown cell. This is going to be the null method. So one, I have to find balance in this circuit, where to find balance, you notice that the positive terminal of the driver cell is joined to the positive terminal of the unknown cell. This is the correct way of joining a potentiometer, of connecting a potentiometer to another cell whose EMF is required, or whose EMF is to be found. The positive terminals must form a common point. Of course, the negative terminals the other side also form a common point. That is the correct way of obtaining a balance. If I was to reverse this cell so that it points in this direction here, I would never get a balance point. There will be no time for which the galvanometer will read 0 in that case. If you connect this in the laboratory, you will also notice it very carefully, that if you don't connect the galvanometer, if you don't connect the potentiometer in this kind of orientation where the positives are linked to the same common point and the negatives are linked to the same common point, you will never get a balance point. So the joker J is tapped at a point near A to see that the galvanometer deflects in one direction, and then to a point near B to see that the galvanometer deflects in the opposite direction, so that we notice that the galvanometer is a two-way deflection, or shows a two-way deflection. Number 2, we now move the joker. The joker G is then moved along AB until the galvanometer shows no deflection, or it points to 0. If we reach a point where the galvanometer points to 0, then this measurement of this length is giving us actually a relationship with this EMF of the unknown cell, because this part of the wire for which the galvanometer gives no reading, this part of the wire is in parallel with this cell. So it's like the PD of this section of the wire must be the same as the EMF of the cell if the galvanometer is giving no reading. This technique is what we call the null method. This technique of finding a point where there is a reading of 0 on the galvanometer is known as the null method. The word null comes from a Latin word nullus, meaning nothing. So the distance Lx is going to be called the balance length. When the instrument reads 0, the distance Lx, or the length Lx, is called the balance length. So the PD across AJ, remember PD is directly proportional to length. So the PD across AJ is going to be equal to a constant times the length Lx. But at balance, the PD across this length is the same as the EMF, because these two are in parallel. This section of the wire of length Lx is in parallel with Ex. So at balance, Vj, or PD across AJ, is going to be the same as Ex. So that means KLx is going to be equal to Ex. So if I want to find K, maybe I can still say K is equal to Ex over Lx. So if I know the EMF of the cell Ex and I don't know maybe the EMF of the driver cell. I know Lx and I know Ex. I can find the PD correspond to that length. And if I know the whole length AB, I can move backwards and I find PD across AB, which will be the same as the driver cell EMF, E naught. So K can also be called the calibration constant, but we shall not talk about the calibration constant now. We just need to know it as a constant. So that's what I'm calling standardization of the potentiometer. But essentially, earlier on we saw that K would be equal to the PD across the wire divided by the length AB. And if the PD across the wire is E naught, we are going to see that K would be equal to E naught divided by the length AB. So we could equate E naught over LAB to EX over LX so that we see that there is a relationship between EMF and length. Okay. So I want you to note that in order to balance the positive terminal of the unknown PD is connected to the positive terminal of the driver cell. So I want to emphasize that we link the positive to the positive to form a common point. If the resistance of the wire is known, then we can calculate the steady current flowing in the slide wire given the EMF of the standard cell. For example, let I be the steady current, the current flowing through the wire. If I is the current flowing through the wire, then at balance, of course, we know that the EMF across, or the EMF of the cell is the same as the PD across AJ, as we have already seen. But remember, PD is I times R, so it means the current flowing through AJ can be obtained from EX, which is equal to VAJ, which is the same as I RAJ. However, do not forget that the PD across AJ is also the same as a constant times the length AJ. That is very important. So let small r be the resistance per centimeter or the resistance per unit length, and Lx be the balance length. And if that is true, then it means the resistance Raj is going to be the resistance per centimeter or per unit length divided times the length Lx, which means the EMF Ex will be equal to the current, because the resistance is R times Lx, where R is the resistance per unit length and Lx is the balance length. So the resistance Aj will be resistance per unit length times the balance length. So when I substitute in this equation here, I times Raj, I get IR times Lx. Hence, I could find the current from the current I equals to Ex divided by RLx, where RLx is resistance of Aj and Ex is actually the PD across Aj, which is the same as the EMF of the unknown cell X. Let's try to compare EMFs using a potentiometer. So let's have two cells. I can close the switch to position 1 and I move the joker along line AB until I get a balance. So I measure the length, which I will call maybe Ls. Then I can close the switch to position 2 and I adjust the joker until I get another balance. I could call that length Ls. The question is, what is the relationship between the EMFs? How are they related? How do we compare the EMFs using a potentiometer? So the EMFs of two cells can be compared using a potentiometer if the connection is like this. Remember, the positive terminals are always linked to the positive terminal of the driver cell. Also, I want you to note that the EMF of the driver cell must be much bigger. Actually, it should be greater than the EMF of these other cells. Otherwise, you may never get balance. So ES is the standard cell and EX is a cell of unknown EMF. With the switch in position 1, the balance point D is located and the balance length Ls is then measured. Of course, if we close this switch here, the PD across L is going to be the same as the EMF. And remember, the PD is equal to a constant times the balance length. So that means ES is going to be K times LS. If S is then connected to position 2 and the balance point D is located again, the balance length Lx is then measured. So it means now when I close to position 2, it means the cell Ex is in parallel with the distance AD, which is Lx. So since V is equal to K times Lx, so Ex is going to be K times Lx. If I combine the first and the second equation, then I will have that Es over Ex is the same as Lx over Ls over Lx. In other words, the ratio of the EMFs is equal to the ratio of the balance lengths. So any unknown EMF can still be calculated for that matter. Any unknown EMF can be calculated if we know that the ratio of the EMFs is equal to the ratio of the balance lengths. Something we need to note very carefully, in determination of the EMF of a cell using a potentiometer, the resistance of the galvanometer is not important because at balance, when there is balance, the reading of the galvanometer must be 0. So we don't need to mind about the resistance of the galvanometer. We don't even need, it may not even be calibrated. After all, it is only going to be useful if it shows no reading. As long as it shows a 0 reading, it is useful. It has shown us balance. As long as we have balance, we don't mind about anything else. So, in determination of the EMF of a cell using the potentiometer, the resistance of a galvanometer is not important because at balance, no current flows through the galvanometer, and if no current flows through the galvanometer, it means there is no PD across the galvanometer. So it means the resistance of the galvanometer is not necessarily needed. Of course, it will be there, but it's not very important. It doesn't also need to be calibrated because the reading is going to be 0 for a measurement to be taken. I want you to note two important things about using potentiometers. The EMF of the driver cell should be greater than the EMF of the driver should be greater than the EMF of the unknown cell if we want to get balance. Number 2, the positive terminals should be connected, positive to positive. Positive to positive should be very important. If we want to get balance, the EMF of the driver cell should be bigger than the EMFs of the other cells. Number 2, the positive terminals should be linked to each other. Let's also see how we use the potentiometer to compare PDs. So the potentiometer technique can also be used to compare potential differences. For example, here we have two resistors. Two resistors could be connected in a series with the cell as shown in the figure here. And the PD across R1 is got by placing the galvanometer in the first position here. We adjust the potentiometer until we get a balance. So we measure the balance length, call it L1. Then we can repeat by placing it at position 2, but now note that the total resistance is going to be R1 plus R2. So this is repeated with the other resistor and the new balance length L2 is found. Then now we can find the ratio of the lengths and the ratio of the PDs. So remember, for the first case, V1 was equal to the PD across the balance length, which was K times L1. And this is the same as, of course, if I know the current here, if I was to load the current here, I would just use the current here, but it will be, of course, the same current, but I don't need that. So V1 is going to be equal to K times L1. Then if I transfer it to this position here, then V2 is also going to be equal to a constant times the length L2. Then I can try to compare the ratio of V1 divided by V2, which will be equal to L1 divided by L2. So we are comparing the ratio of the PDs is equal to the ratio of the length. So by comparing, the ratio of the lengths is going to be equal to the ratio of the PDs. That's number one. Since both resistors have the same current, because they're in series, then it also means that the ratio of the PDs is also equal to the ratio of the resistances. In other words, the PD across R1 divided by the PD across R1 plus R2 is the same as K over KL1 over KL2 when you divide, which is going to be the same as I R1 over I into R1 plus R2, because the same current flows through them, and PD is equal to current times resistance. So for the first one, it's going to be I times R1. For the second one, it is going to be I into R1 plus R2. That is from Ohm's law, V equals to I times R. So it means the ratio of the PDs is the same as the ratio of the lengths, which is the same as the ratio of the resistances. Putting in mind that in the second position, that is in the green, the total resistance is R1 plus R2. Okay, so that is potentiometers, using them to compare EMFs and to compare PDs. Example: to make a potentiometer, a driver cell of EMF 4 volts is connected across 1 meter length of resistance wire. What is the PD across 1 centimeter length of the wire? Of course, 1 meter is 100 centimeters. So if I want the PD across 1 centimeter, that is a constant, which is going to be 4 divided by 100, which is 0.4 volts per centimeter. 0.4 volts per centimeter. Then what length of wire has a PD of 1 volt? So remember, V is equal to the PD per centimeter times the length. So the V is 1.0, the PD per centimeter is 0.4 volts over centimeters times L. So it means that L is going to be equal to 1 divided by 0.4. 1 divided by 0.5, I think it is 25 in centimeters. So I think that is correct. A cell of unknown EMF E is connected to a potentiometer, and the balance point is found to be 37 centimeters from the end of the wire to which the galvanometer is connected. Estimate the value of E. Okay, so I think 4 divided by 100 is 0.04. Sorry. I'm very tired. So this is 0.04 volts per centimeter. Okay, estimate. If the cell is connected to the potentiometer, of course we know from what we have already discussed, the EMF of the cell is equal to the PD across the balance length. The PD across the balance length is the constant times the balance length, called Lx. So Ex is the constant, which is the PD per centimeter, times the balance length. So this would be K, which we have got as 0.04 volts per centimeter, times the balance length, which is 37 centimeters. I think this gives us 1.48 volts. Okay, estimate the value. Explain why this can only be an estimate. Of course, this can only be an estimate because the driver cell will have an internal resistance. That one we know. The driver cell of 4 volts may be having an internal resistance, so it means if it has an internal resistance, then it means the PD across the wire may not be 4 volts, which means K is just an estimate in the first place. The PD across the terminals and the wire will be slightly less than 4 that we have used to find the constant K. So because of the internal resistance, the driver cell may have an internal resistance and it's supplying current to the potentiometer wire. Therefore, the PD across its terminals and the wire will be slightly less than the EMF we have chosen to be we have considered 4 in the first part or in part A. A standard cell EMF 1.23 volts gives a balance length of 31.2 centimeters. Use this value to obtain a more accurate value of E. So we saw that there's a relationship between the EMFs connected to a potentiometer. First of all, we know that the first one, EMF EX, was equal to K times the balance length, which was 37.0 centimeters. Then the second standard cell has EMF 1.23, and this should be equal to the constant K times the balance length, which is 31.2 centimeters. So this one avoids us from using the constant K because we can divide the two equations. So it means EX divided by 1.23 is the same as 37.0 divided by 31.2. The centimeters cancels out. So remember, this is in volts. So this is going to give us 37 divided by 31.2, then times 1.23. So this is giving me EX as being equal to 1.46 volts. So if we use this as a standard cell, then we ignore using the constant, yet since we have assumed that the driver cell could be having an internal resistance, which may end up affecting our results or our values that we have obtained. Okay, example maybe 2. In a potentiometer experiment, the balance length of a wire is 53.4 centimeters when the standard cell of 1.08 volts is used. The balance length with cell X is 72.6 centimeters. Calculate the EMF of cell X and draw a complete sketch. Draw a complete sketch of the circuit arrangement. Okay, of course, this is very simple. The circuit arrangement, we have already seen such a circuit. We already had it. So remember, we have already seen that the ratio of the EMFs is equal to the ratio of the balance length. So I can just think about that precisely. The ratio of the EMFs, ES divided by EX, is equal to the length for S over the length for X. So calculate the EMF of cell X. So EX is going to be the balance length for cell S, which is 53.4, divided by that for cell X, which is 72.6. No, I think that is wrong mathematics. I have to reverse this. I'm making EX the subject, so I have to get the reciprocals. So EX is going to be LX, which is 72.6, divided by LS, which is 53.4 times ES, which is 1.08 volts. So I have 72.6 divided by 53.4 times 1.08, which gives me 1.47. Seventy-two point six divided by 53.4 times 1.08, 1.47. So the EMF is going to be 1.47. Okay. So the PD per centimeter, which is a constant, we saw it is K with the switch connected to position 1. Of course, we have already derived this. LS was that. So we saw that ES is equal to K LS. In other words, 1.08 is the same as length times the constant. And with the switch in position 1, the position 2, the balance length was 72.6, and this gave us an equation like that. So we just divide the two equations. So we have that EX over 1.08 is equal to 72.6 over 53.4 times K. The K cancels out. So this gives us, I think this is 1.47, not 9. 1.47 volts. So it means the EMF of the cell is going to be 1.47 volts. Okay. Example 3. In the figure above, or in the figure besides, AB of length 1 centimeter has a resistance of 10 ohms. If point C is the midpoint of AB, so C is the midpoint, and the voltmeter reading is 2 volts, find the value of R. So find the value of R. So if this is the midpoint, of course it means the resistance of SC should be the same as the resistance of CB, because resistance is directly proportional to length. So if this has been divided into two parts, then the resistance of SC should be the same as the resistance of CB. And the whole resistance of the whole wire was 10 ohms, I think. AB is 1 centimeter, has length of 10 ohms. So it means, since resistance is directly proportional to length, it means the resistance of AC is going to be half of 10, which is going to be 5 ohms. The resistance of CB is going to also be 5 ohms. Then the PD across SC is going to be the same as the PD across R, because SC, this portion here, is in parallel with the resistor. So the PD across S is going to be the same as the PD across R, which is given as 2 volts. So because they're in parallel, which means therefore, because the PD here is 2 volts, the PD here is going to be 6 minus 2, which is going to be 4 volts. Then we can now use Kirchhoff's laws if we want. We can use Kirchhoff's laws, and from Kirchhoff's laws, it means at this point here, because the PDs are different, so it means at this point here, the current is actually dividing. Therefore, the current from C to B is going to be the total current in the circuit, which continues this side. So that current is dividing at point C. So the current CB is the same as the current from A to C plus the current which comes from the resistor here. So this is I, R, and here we have IAB. So it is, ISC. So it's going to be ISC plus the current from the resistance R. That is in accordance to Kirchhoff's first law. So the current from ICB, remember I equals to V over R. So this one is going to be 4 divided by its resistance, which is 5, should be equal to the current in SC, which is going to be the PD, which is 2, divided by its resistance, which is 5, plus the current in R, where the PD is 2 over the resistance, which is R. I think this can give us R. So here we just make R the subject, 4 over 5 minus 2 over 5. Then I get the reciprocal times 2. So R is 5 ohms. Therefore, R will be 5 ohms. Okay. Okay, so in my solution, I say the resistance SC is the same as the resistance CB, which is 5 ohms. I've already mentioned that. And then the PD across SC is the same as the PD across R, which is 2 volts, because those two parts are in parallel. which meant that the PD across CB is 6 minus 2. That is the balance of 6, which gives us 4 volts. And if I use Kirchhoff's first law, ICB is the same as ISC plus IR. And when I just substitute, I get R as being equal to 5. Alternatively, from Ohm's law, that is from V equals to IR, I is V over R. That one you should note very carefully. That's why I say that the current from R is 2 over R, and the current from ICB, or the current through ICB, is 4 over 5, where 4 is the PD across ICB and 5 is the resistance of CB. And the current from SC is 2 over R, where 2 is the PD across SC and the resistance is 5. That's why I combined these to get my equation, which when solved, it gave me R as 5. I think I got this also from past papers. Okay, I think that should be the end. Next is going to be self-check for you to practice. You can pause the video and try to see if you can solve these questions. So you can solve question 1 and 2. You can always write to me a message to give you a hint where possible or where you have a challenge. Solve question 3. Of course, we have answered question 3A, the advantage which circuit 1 has over circuit 2. For circuit 1, when the PD is 0, the current will be 0. The PD across, when the fixed resistor or when the variable resistor is 0, the PD across the bulb will be 0, so the bulb will be off. And then when the fixed resistor is maximum, the PD across the bulb will be maximum and the bulb will be very bright. So we have a full range of brightness. That's an advantage compared to circuit 2, where circuit 2 we have just a minimum which doesn't go to 0 and a maximum. So you can answer question 3. Then you should be able to answer question 4. And you should be able to answer question 5 finally. And that marks the end of electricity and DC circuits. Do not forget to watch the solved past paper questions.